All right, and then here is an example of cyclic integration by parts, which is a really cool idea where you feel like you're not getting anywhere with your integration by parts, but you actually end up somewhere nice. So, for example, let's say I'm trying to do the integral of sine of x times cosine of x dx. You can do this integral by using substitution, but you can also do it by doing cyclic integration by parts. So, for example, I could say let u equal sine of x and dv equal cosine x dx. It's pretty arbitrary which one you choose. So then du is equal to cosine x dx and v is equal to sine of x. So you see that this is equal to u times v minus the integral of v is sine of x v times du. And so what I noticed here is that the original integral I shows up again right here. So what we have is I equals sine of x times itself minus I. In other words, 2 times the original integral is sine squared of x. I just added I to both sides of the equation. And then if you divide by 2, you get that your integral is equal to sine squared of x over 2. Of course, you have your plus c. So we just showed, using cyclic integration by parts, that, I guess I didn't need to cross that out, we just showed that the integral of sine of x cosine x is equal to sine squared of x over 2 plus c. We could have done it using just substitution, because if you make u equal sine of x, then its derivative shows up as cosine x dx. And so you could have done it like this. U du becomes u squared over 2 plus c. Same thing that we had right down here. It's just another way of getting to it. I'll show one more example of cyclic integration by parts where you have a trig function and an exponential function. So that last one was just kind of a different technique. It's not like the easiest way to do it, but you could use cyclic integration by parts for a problem like this. There's no substitution that's going to help here. So let's just do cyclic integration by parts will help. Du is going to be 2e to the 2x dx. V is going to be negative cosine x. So we have u v minus the integral of v du. Switch the negatives to positives. Now it's important that whatever choice you made here for u and v is sort of the same choice you're making over here. So I'm going to say u is 2e to the 2x, and dv is cosine x dx. So du is 4e to the 2x dx, and v is sine of x. So now we have e to the 2x cosine x plus u times v minus the integral of v du. And you can recognize here our original integral showing up here times 4. So what we have is the integral is equal to all of this minus 4i. So what I do is I add 4i to both sides of the equation, and I have 5i equals negative e to the 2x cosine x plus 2e to the 2x sine of x. And then I know that my integral I is equal to all this stuff divided by 5. And the crazy thing, plus c, the crazy thing is that you can verify this by actually taking the derivative, and it should come back to be the original piece. So let's try that out. So I'm going to do the derivative of the whole thing we have there, and we should get back to just e to the 2x times sine of x. So let's try. We're saying negative e to the 2x cosine x plus 2e to the 2x sine of x over 5. Let's take the derivative of all this fun stuff. So we'll do a couple product rules. So we have negative 2e to the 2x cosine x, that's like f prime g, plus negative e to the 2x times negative sine of x, plus 4e to the 2x sine of x, plus 2e to the 2x times the derivative of sine, cosine x. And all that is divided by 5. And what I notice when I look at this is we have a negative 2e to the 2x cosine x. And we have a positive 2e to the 2x cosine x. See you later. Here we have a double negative, e to the 2x sine of x, and 4 more of them. So somewhat amazingly, we have 5e to the 2x sine of x over 5, which equals the original value. So it's kind of nice. So that's cyclic integration by parts. Please let me know if you got any questions. Happy to help out. Thank you for watching.